Hello everyone, myself Melvin Mathew, currently pursuing MCA at Marian College Kuttikkanam, Autonomous. Today I am going to talk about the PageRank principle, navigating the web through graph theory and operations research. The PageRank algorithm was created by Larry Page and Sergey Brin, the founders of Google. The basic idea is that the internet can be viewed as a network of connected web pages. Each web page links to other web pages. Using graph theory, we can analyze these connections and determine which pages are the most important or influential. This mathematical approach became the foundation of modern search engines. The internet is a graph, not a library. In a library model, information is stored like independent books on shelves, but the internet is different. Web pages are connected through hyperlinks, forming a large network. Instead of reading every page, search engines look at the connections between pages. By analyzing these connections, algorithms can determine which pages are the most relevant and trustworthy. To apply mathematics, the web must be converted into a graph structure. In this structure, a node represents a web page. A directed edge represents a hyperlink from one page to another. Two important concepts here are in degree, which is the number of incoming links to a page, out degree, which is the number of outgoing links from a page. Pages with many important incoming links tend to have higher importance in the network. PageRank is based on three key principles. The first principle is volume. This refers to the number of incoming links a page receives. More links generally indicate higher importance. The second principle is quality. Links from highly trusted or important pages carry more weight than links from unknown pages. The third principle is probability. PageRank models the probability that a random user browsing the web will eventually land on a particular page. These three factors together determine the final ranking. Behind PageRank is a strong mathematical engine based on Markov chains and matrix optimization. The web graph is converted into a probability transition matrix, which describes how users move from one page to another. Using operations research techniques, the system repeatedly performs matrix calculations. These calculations continue until the values stabilize, producing a final ranking hierarchy. This process allows search engines to compute the importance of billions of web pages. This shows how Google solved the problem of ranking web pages. The problem was simple but massive. How do you rank millions of web pages instantly for each search query? Google approached this in three steps. First, they used graph theory to map the web as a directed graph. Second, they used operations research to solve matrix eigenvalue problems and compute page rank scores. Third, they added machine learning to improve search relevance. The result was faster retrieval and more reliable search results. This mathematical approach works extremely well for several reasons. First, it provides high accuracy, ensuring that important pages naturally appear higher in search results. Second, it works at massive scale, processing billions of nodes and trillions of links. Third, it supports dynamic updates, meaning rankings adjust automatically as the web grows. Fourth, it helps detect communities and topic clusters, which improves recommendation systems. Finally, it reduces manipulation from fake backlinks and spam. One of the most powerful ideas behind PageRank is that it is a universal blueprint for ranking networks. Even though it was designed for web pages, the same mathematics works for any connected system. As long as we can define the nodes, the entities in the system, and edges, that is, the relationship between them, we can apply PageRank to rank importance within that network. This shows how graph theory and PageRank ideas are used across industries. In Google search, nodes are web pages and edges are hyperlinks. In YouTube, nodes are videos and edges represent clicks or watch history. In social media, nodes are accounts and edges represent follows or interactions. In financial systems, nodes are bank accounts and edges represent transactions. In each case, graph algorithms help identify importance, recommendations, or suspicious patterns. In social platforms, Graph algorithms help analyze interactions between users and content. By studying these connections, platforms can calculate influence rankings, identifying the most influential users and trending posts. The same network analysis is used for predictive recommendations, suggesting content that a user is most likely to watch or engage with. This improves user experience and keeps platforms dynamic and personalized. Graph analytics is also used in banking and financial systems. Banks treat financial transactions as a directed graph, where accounts are nodes and transactions are edges. Using graph algorithms, systems can detect suspicious patterns such as money laundering loops, network of fake accounts, unusual transaction flows. This helps financial institutions improve fraud detection and financial security. To conclude, PageRank demonstrates how graph theory and operations research can solve complex real-world problems. These mathematical principles transformed how search engines organize information and navigate the web. Today, the same ideas power recommendation systems, social networks, financial fraud detection, and many other applications. This shows that graph analytics is not just theoretical mathematics. It is a fundamental technology behind the modern digital world. Thank you.